Hey students, welcome to lecture number 7 of Linear Algebra 2. So today we start a new topic, namely we will talk about eigenvalues and eigenvectors. So last time we talked about the determinants of linear maps. So if we had a linear map from one vector space V to itself, then we could assign to this linear map a determinant which was a real number, and this determinant told us if this linear map is invertible or not. And these new objects we want to study, these eigenvalues, they will also be some important property of linear maps, and they also appear in a lot of applications, which we will discuss later. But the main idea today is to introduce eigenvalues and eigenvectors and to understand how to calculate these for explicit linear maps. And the main goal behind this is to understand linear maps from one vector space V to itself, and somehow the strategy to understand linear maps and to describe them nicely is to study certain subspaces. So somehow the strategy study subspaces which are invariant under this linear map, meaning study subspaces U in V such that if I apply this linear map to the subspace, then I am again in this subspace U, so this means that they are invariant under this linear map. And one special case is when this U is a one-dimensional subspace, and this is really an important case. So when U is one-dimensional, so this means it is spanned maybe by some vector U. Let's say U is not 0, then being invariant under this linear map means that if I apply f to this small u, then this is again a multiple of u, because it stays in the same subspace, which is one-dimensional. So let's say maybe u in this case is the span of this u. And if this subspace is invariant under this linear map, this means that if I apply f to u, then this is just some multiple times u, so it just gets stretched somehow in this direction of u, and this lambda here is a real number. And these subspaces are interesting, and these vectors u and lambdas, and this is one example so of an eigenvalue and eigenvector. So this number here, this lambda, will be called an eigenvalue, and this u will be called an eigenvector. And we will see that it's quite interesting to understand the eigenvectors and eigenvalues of a linear map, and also these subspaces, and knowing these subspaces which are invariant under this linear map f can help us to understand what this linear map f is actually doing to the whole space. And these eigenvalues and eigenvectors, as I said, appear in a lot of applications. So for example also in physics and also in computer science. But we will start now with the pure mathematics. So we will first start with some simple example. So let's consider this linear map here, which is a linear map from R3 to R3, given by a multiplication of this vector A. So A is this 3 by 3 matrix here. And in this case, I will give you a subspace or two subspaces which are invariant under this map. So first notice that if I give you this matrix here, then maybe it's not clear to you what this linear map is actually doing. But now let's define the following subspace U, which is the span of these two vectors, 1, 1, 0 and minus 1, 0, 1. Let's call them U1 and U2. So this is a subspace of R3, and it's spanned by two vectors, so it's just a plane. And you can check that if you apply this linear map to these vectors, so for example if you multiply this vector with this matrix, you get exactly the same vector back. So this means that this satisfies f of u equals 1 times u for all u in this subspace capital U. So for this you just need to check that this holds for these two basis elements of this subspace U by just multiplying these vectors with this matrix. So we have this subspace, so this linear map somehow leaves this plane untouched. So if you apply f to this plane, it will just stay there at the same place. And then let's consider this subspace L, which is now the span of this vector 1 minus 1, 1, which I will call U3. So this is a line in R3, so this is also a subspace in R3. And if you multiply this vector with this matrix, what you will see is that you get the negative of this vector. So this satisfies f of w is minus w for all w in this subspace L. So we have now one subspace which is a plane which stays invariant under this map f, and there's one line, and each point on this line gets mapped to its negative, so it's still also in the subspace L. It just points in the opposite direction. And now you also notice that if you look at these elements in the plane and on these lines, that these things are orthogonal on these, meaning if I have this plane here, then this line L is orthogonal. So, and this we did in linear algebra 1. So there we define the orthogonal complement, and in this case the orthogonal complement of this space U is actually this L. So this means that all vectors in U are orthogonal to L, and this we just need to check for the basis elements. So you can check that if you take the dot product of U1 with U3, this is the same as the dot product of U2 with U3, and both of them are just 0. And also being the orthogonal complement, we learned means any vector in R3 can be written uniquely. So there's just one way to do this. So x can be written as some u plus some w, where this u is in the subspace U and this w is in the subspace L. So let's get this picture here. So U is a plane, it's a two-dimensional subspace, which we can see here, and L is orthogonal and one-dimensional. So L is orthogonal to U and it's one-dimensional. And any element in R3, for example this x here, can be written as the sum of some U plus V. So the picture looks like this. And now if we apply this linear map f to this x, then because f is linear, this is f of u plus f of w. But we just checked that this linear map f, so everything on u just stays the same, but everything in L gets mapped to the negative. So this means f of u is just u, and f of w is minus w. So we get this thing here. And here in the picture, this means that this element here, u minus w, is we go to u, oops, and then we subtract w, so we go here, and this will be f of x. So already this now gives all information on this linear map f, namely that f, what it does for an arbitrary vector x, is it gives a reflection among this plane U. And these kinds of linear maps we also discussed in linear algebra 1. But the main point here is that knowing these two subspaces, which are invariant under this map f, enables us to already describe this this whole linear map F. And these vectors which satisfy these properties, like here this u is invariant under this F and this w gets mapped to its negative. As we said in the beginning, these will be called eigenvectors and eigenvalues, and the precise definition is this here. So if I have a linear map F going from one vector space to itself, then lambda is called an eigenvalue of this linear map F if there exists a vector which is non-zero, such that F applied to this vector is lambda times this vector. Also notice that this of course is always true if this v would be 0, so that's why we exclude this. But if v is non-zero, then there's exactly one lambda for which this is true if such a v exists. And if I have a vector v which is non-zero, which satisfies this property with this lambda, then this is called an eigenvector of F with eigenvalue lambda. So in the example we did before, we had two eigenvalues. So one eigenvalue was given by 1, so this is an eigenvalue of the F in the example we did. Since we could find a vector which is non-zero, for example this u1, which was one of these, so u1 was just this vector here, and f of u1 was just u1. So this was an example of, or more precisely, this is lambda 1 times u1, so it's just u1. So this lambda is an eigenvalue, and this u1 is an eigenvector. And also this u1 was not 0. So this is an eigenvector. And also we had the eigenvalue -1. Because f of u3 was -u3. So this u3 is also an eigenvector with eigenvalue -1. Okay, and also notice that every vector in the subspace U, so in fact any vector in the subspace U, where if we take except for the 0 vector, is an eigenvector with eigenvalue 1, and also any w in this L, if w is not 0, is an eigenvector with eigenvalue -1. So because here we checked that u1 and u2, the two basis elements of U, were eigenvectors with eigenvalue 1, and then if I have any U, which is some linear combination, let's say alpha 1 times u1 plus alpha 2 u2, then if I apply f to this, f of this is, well, I can apply f to u1 and u2, but this will just give back alpha 1 u1 plus alpha 2 u2. So this is just u. So you see that any linear combination of eigenvectors to the same eigenvalue will also give an eigenvector to this eigenvalue, if it's non-zero. Okay, but in this example, I gave you the eigenvectors, and you then could check that they are eigenvectors to these eigenvalues 1 and -1. But usually in the application, you just have the linear map, and then you should calculate what are the eigenvalues, and then calculate the eigenvectors. So this is so now it's a question: how do we actually calculate eigenvalues and eigenvectors of a linear map? So for this, so let's start by saying that lambda is an eigenvalue of this linear map F. So this means that we can find a vector v which is not 0, such that f of v is this lambda times v. But this we can also rephrase. This means there exists a non-zero vector v such that f minus lambda times the identity on the space v applied to the small v is 0. And here this identity v is just the linear map which just sends the word w to w. And clearly if I have this condition here, this is equivalent to saying that that this linear map here, f minus lambda times the identity of v is 0, is exactly the same as saying that f of v equals lambda times v. Because v is just identity on this vector space v applied to this vector v. And now we see we have the condition here is exists a non-zero element such that this linear map applied to this is 0. And the elements which gets mapped to 0 of a linear map are exactly the elements in the kernel. So this means there exists a non-zero element which is an element in the kernel of this linear map. But this means, so if there's a non-zero element in the kernel, this means that the kernel is more than just the 0 element. So this means the kernel is not just the 0 vector. I mean, 0 is always in the kernel. And this means, well, this means that this map here is not injective, but we consider the case that we have a linear map f from one vector space to itself, and in this case being not injective is equivalent to being not isomorphic. So this means that if this map is not injective, meaning the kernel is not just 0, this means that this map is not invertible, and being not invertible, we learned, means that the determinant of this linear map is 0. So this means that the determinant of this linear map is 0. So this here, there are two statements. So we had this one theorem 2.5. In 2.5, the last point of the theorem stated that if I have a linear map from one space to itself, then the conditions that f is invertible is equivalent to f is injective, which is equivalent to f is surjective. So in particular here, this is equivalent. Being not injective means it's not invertible. And then we also had this theorem 4.11, which states that being not invertible is equivalent to the determinant is 0. And now we have the determinant of a linear map, and this means what is the definition of the determinant of a linear map? This was defined by choosing any basis. So if B is a basis of V, then the determinant of this linear map was defined by the determinant of the matrix attached to this linear map with respect to this basis B. But so this coordinate vector here which basically just meant we multiply by these change of basis matrices. So this is linear, and this gives the, so we can take just the matrix of F with respect to B minus, and the matrix of the identity map is the identity matrix. So here it's lambda times the identity matrix In. So here in this case the dimension of V is n. So therefore this statement here, the determinant is 0, means that the determinant of this matrix here is 0, and all this now is in the case when V is finitely generated, meaning the dimension is finite, in this case n. So, in other words, if lambda is an eigenvalue of this linear map F, this is equivalent to that this determinant of this matrix here is 0. And so let's do this for our example. So there we have explicitly given this linear map F, and then we need to subtract this lambda times identity matrix and calculate the determinant, and then see for which lambda this determinant is 0. But first, let's summarize this. So the eigenvalues of F are given by the solutions of this determinant of F minus lambda identity, which is the same as this here, is 0, and then the eigenvectors for such a lambda are then given by the, so what are the eigenvectors in this picture here? Well, here this V is the eigenvector with respect to this eigenvalue lambda, and these are the elements in this kernel here, and this being, when this determinant is 0, this meant exactly that this kernel is non-zero, so the non-zero elements in this kernel are exactly the eigenvectors for this eigenvalue lambda. So the eigenvectors for lambda are given by the non-zero elements in the kernel of F minus lambda times the identity. Okay, but now let's do this in our example to see how this actually works. So again, it takes the same linear map, and now so we have the linear map F given by this matrix here. So in this case, this A is the matrix of this linear map F, and we now want to calculate the eigenvectors, the eigenvalues. So let's calculate the eigenvalues. So we want to find the solutions of the determinant of A minus lambda times I3 equals 0. Because in this case, the dimension of V is 3, and A is a matrix of F, and therefore we want to solve this equation here. So how many times do I need to subtract the identity matrix from this matrix A such that the determinant is 0? So let's write this down. So what is A minus lambda times identity? Well, this is the determinant of, okay, so this is 1/3, 2/3, minus 2/3, 2/3, 1/3. Oops, thirds. And I subtract lambda times the identity, meaning I have lambdas on the diagonal and 0 here. So, well, what is this? This is determinant of, so it's 1/3 minus lambda here, 2/3 minus 2/3, 2/3, 1/3. Oops, here I forgot the lambda. So on the diagonal we just subtract the lambda. And 1/3 minus lambda. So we want to calculate the determinant of this 3×3 matrix and then see what are the values for lambda such that this is 0. And now there are several ways we can calculate the determinant. So for example, we had an explicit formula for 3×3 matrices. So for example, I can take this times this times this, plus this times this times this, plus this times this times this, minus this times this times this, minus this times this times this, minus this times this times this. So we had this explicit formula, and you see this will give an explicit expression which is a polynomial in lambda. But in this case, let's do it a little bit more systematic, or also in another way. And so first, notice that this 1/3 here is a little bit annoying. So we could what we learned in last time is that the determinant is linear in each row. So I could factor out this 1/3 in the first row and put it in front of the determinant. And I could also factor out the 1/3 in the second row, put it in front, and the 1/3 in the third row, put it in front. So in total, I can factor out 1/3 to the power 3, and get that this is the same as the determinant, where I multiply everything by 3. So here it's 1 minus 3 times lambda. It's 2 minus 2, 2, 1 minus 3 times lambda, 2 minus 2, 2, and 1 minus 3 times lambda. Okay, you could also see it like this. We learned that the row operation, which multiplies a row by some factor, for example, if I multiply this by 3, then the determinant will change by this factor 3. So I need to divide by 1/3 to such that I don't change anything here. But you can also think like that the determinant is linear in each row. And this is what you proved in your homework. And now, so still maybe it's not easy to calculate this determinant here. So what we can do now is, for example, add this row to this one times, and also subtract this from the first one. So this is row operation 1, which doesn't change the determinant, because adding a multiple of one row to another doesn't change the determinant, so it's still 1/3 to the power of 3 times the determinant. And if I add, so if I subtract this row from this row, what I get is minus 3 times minus 3 lambda, 0 minus 3 plus 3 lambda. This I get here, and if I subtract this one from there, then I get a 0 here, and if I add this one to this, then this gives 0, and here I get a 3, so it's 3 times minus 3 times lambda, Oh, and here I also did a mistake. So this is a plus. So here minus times minus is plus. So here I have a plus 3. And here I have 3 minus 3 times lambda. And here I still have the same, like this. And now again, here you see the factor 3 minus 3 lambda, which I can factor out. And also I can factor this out in this row here. So this is the same as 1 over 3. And here I have 3 minus 3 times lambda squared. And now here I have 1, 0 and minus 1, 0 and 1 and 1, and here minus 2, 2, 1 minus 3 times lambda. Because again I used that the determinant is linear in each row, so one time I can factor out this 3 minus 3 times lambda to get this row here, so I get 1 time this factor, but I can also factor this out here, so I get this factor squared. And also now here you see that I can cancel out these two 3's, so I can write 1 minus lambda here, and I can remove the cube here. And so now we just need to calculate the determinant of this here. And well, for this I can so I can get rid of these by adding this 2 times there and subtracting this 2 times there. So I again use row operation 1. So let me write this down here maybe. So 2 times I add this there and minus 2 times this there. So I get the determinant of 1, 0, minus 1, 0, 1, 1. And here I get a 0, 0. Here I get minus 2 here, so it's a minus 1. And here I get a minus 2, so it's a minus 3. So it's minus 3 minus 3 times lambda. And therefore the determinant of this matrix here now is just the product on the diagonal. So this is just 1 times minus 3 lambda. So this is 1/3 1 minus lambda squared times minus 3 lambda. So in other words, I can cancel out this 3 here. So this is 1 minus lambda squared. And here if I rewrite this, this is 1 plus lambda. And I put this minus sign here in front. So this is the determinant of this matrix here. And to find the eigenvalues, we need to ask, when is this determinant 0? So in other words, when is this expression here 0? Well, but in this case, it's easy to see when this is 0, because the product of polynomials is 0 when one of these factors here is 0. So either this lambda is 1, then this factor is 0, or if this lambda is minus 1, then this factor is 0. So in other words, the determinant of a minus lambda times I3 is 0 is equivalent to lambda is 1. Oops. Lambda is 1 or lambda is minus 1. And there are no other solutions to this. That's the only case when this thing can be 0. So, in other words, the eigenvalues of f, also of this matrix A, are let's call them lambda 1 is 1 and lambda 2 is minus 1. Okay, so these are the eigenvalues, and now what are the eigenvectors? So we know now that if I use one of these two lambdas, then this matrix here has a kernel which is not just 0, but there are more vectors inside, and these non-zero vectors are the eigenvalues for this lambda. So let's calculate them. So here now the eigenvectors. So let's consider the case lambda 1 is 1. So in this case we want to calculate the kernel of A minus lambda times identity matrix, so in other words lambda minus I3. So what is A minus I3? Well, what was A? Let's maybe just copy this one here. Oops. I want to do it like this. So we want the case where these lambdas are 1. So this is A minus 1 times the identity matrix. So in other words, this is, so 1 minus is minus 2/3, 2/3, minus 2/3, 2/3, 1 is minus 2/3, minus 2/3, 2/3, and minus 2/3. But here now you see that this is exactly the same as this, and this is a negative. So if I do this row operation by adding this one to this and subtracting this one to this, then this matrix is row equivalent to minus 2/3, 2/3, minus 2/3, 0, 0, 0, 0, 0, 0, which is row equivalent by multiplying this by minus 3/2. This is just 1 minus 1, 1, 0, 0, 0, 0, 0, 0. So this matrix is row equivalent to this. And now to calculate the kernel of this matrix, well, it has the same kernel as this matrix here. So if we think again about linear systems, what is the linear system behind this? Here we see we have two free variables, and so the kernel in this case is something two-dimensional. So the kernel of A minus I3 is the span of 1, 1, 0, minus 1, 0, 1. So here I choose two free variables, and then the first one you will see, so if I have a free variable t1 and t2, then here t1 times this plus t2 times this vector give all solutions. So the kernel is the span of these two vectors, which are exactly what we had before. The span is, so the kernel in this case is exactly this plane which we denoted before as U. Okay, and for the eigenvalue lambda 2 is minus 1, we need to calculate, we want the kernel of A plus I3, plus because it's minus 1 times I3. So A plus I3 is, so we have this matrix here, but we add in -1, so we add +1 here. And there you can check that this is row equivalent. So I do it in the lecture notes, but this is row equivalent to this matrix here. So in this case, we just have one free variable, and therefore the kernel of this is just the span of one vector, namely 1, -1, 1. And this is what we called L, this space L, this line before. Okay, so these are the eigenvectors for these eigenvalues. So again, let's recall, we started with the linear map F given by multiplication with this matrix here. And first we calculated the eigenvalues by subtracting lambdas on the diagonal of this matrix, and then calculated the determinant, which in the end gave us this polynomial. And then we needed to find the zeros of this polynomial, which in this case gave us two solutions. And then for each solution we plugged this solution in and calculated explicitly what is the kernel of this matrix. And then in this case, in the case when the eigenvalue was 1, we got a two-dimensional kernel. And in the case when the eigenvalue was -1, we got a one-dimensional kernel. And in general, this determinant if I have a linear map, then the determinant of f minus lambda times the identity map on this. So let's say again the dimension of V is n. Then, I mean, what is this by definition? This is the sum over all permutations. So let's say this matrix is a matrix with entries b, I, j. So let's say we have some basis b, and we have the entries b, I, j here. So we have b, j, sigma j. And if the matrix of F, which in our example was A, is given by the entries A, I, j, then these Bij's are, so the Bij's are the same as Aij's if the I is not j, and if I equals j, so on the diagonal we subtract lambda. So therefore, if you look at this formula here, then here we multiply these entries b, so we multiply these factors here, and so we always will get a polynomial in lambda, and the degree of this polynomial, because here the factors can be up to n factors, meaning this is always a polynomial, so this is a polynomial in lambda of maximal degree n, where n is the dimension of this vector space V. And the eigenvalues are the zeros of this polynomial. Okay, and also because the matrix of a linear map is independent of the choice of the basis, this means this polynomial is really some property of this. So we can assign to this linear map a unique polynomial, this one here, and then the eigenvalues are the zeros of this polynomial, and that's why this polynomial also gets a name. and this is called the characteristic polynomial of f. So let's be more precise. So if f is a linear map from V to V, and this is the identity map on V, and also this V is always finitely generated. So let's say the dimension of V is n. Then we write f of this capital F of lambda as the determinant of this f minus lambda times the identity, and this is called the characteristic polynomial of f. And also these kernels, if we have an eigenvalue lambda and then these kernels of f minus identity of minus lambda times the identity, these are also, they get a name, and these are called the eigenspace of f with respect to the eigenvalue lambda. So if we have an eigenvalue lambda of a linear map f, then we write E lambda of f as the kernel of f minus the identity. So in other words, these are exactly the vectors in V with the property that f of v equals lambda times v. So the eigenspaces consist of all eigenvectors with this eigenvalue, plus they also contain the zero vector, even though we don't call the zero vector an eigenvector, but here the zero vector is of course contained in the kernel. So maybe let's mark this here. So this contains all eigenvectors of f with eigenvalue lambda and the zero vector. And also with this discussion here, because this polynomial, this characteristic polynomial is a polynomial of degree n, and from calculus you know that a polynomial of degree n can have at most n zeros. So this means that a linear map from a n-dimensional space to an n-dimensional space can only have up at most n eigenvalues. So the degree of this characteristic polynomial is n, the dimension of v, and this means f can have at most n different eigenvalues. So let's go back to our example. In our example, we were in the case when n is 3, because this is 3-dimensional. So here we see our polynomial, so which we can now give a name. So this is now, so this polynomial here is now f of lambda. This is a polynomial of degree 3. And so we could have up to 3 zeros, but in this case we just have 2 different zeros. But here this 0 has multiplicity 2. And also these spaces here, so in this case this u, let's write it here, this is now the eigenspace to the eigenvalue 1 of f, and this L is the eigenspace of the eigenvalue minus 1 of f, and so an f can have at most n different eigenvalues, but it could also be the case that this polynomial actually has no zeros, so f could have no eigenvalues. And so, for example, this matrix here 1 minus 2 to 1, let's say this is A. What is the determinant of A minus lambda I2? This is determinant 1 minus lambda minus 2 to 1 minus lambda, which is 1 minus lambda squared plus 4. And you can check that this polynomial, I mean, if you would plot this, what is this? This is, so it's somehow this parabola here, and this actually has no zeros. So this has no eigenvalues. So in our case, at least, it has no real eigenvalues. And but also some matrices maybe just have exactly one eigenvalue. So for example, the identity matrix has just the eigenvalue 1, and also this matrix here, you can check, has one eigenvalue, also 1. But sometimes we get n eigenvalues. So for example, this matrix here, the diagonal matrix with the entries 1 and 2, you can check that if we have a diagonal matrix, then with entries, in this case 1 and 2, then you have, in this case, 2 eigenvalues, which are 1 and 2. Because in this case, if I multiply this with the vector 1, 0, it's just 1, 0. And if I multiply it with the vector 0, 1, then this is 2 times 0, 1. So if you have a diagonal matrix with n different entries, then you will also have n different eigenvalues, because multiplying with these standard vectors here, the unit vectors, you always get this diagonal entry times this vector. Okay, so this was the introduction to eigenvectors and eigenvalues. And in the homework you will calculate some examples, and next time we will talk about more why eigenvectors and eigenvalues are interesting. So for example, in the exercise with the Fibonacci numbers, you already saw that you needed to calculate some vectors such that if you multiply the vector with the matrix, it was just a multiple of this vector, and then these vectors, taking them as a basis, and then write down the matrix of this map with respect to, or write down the matrix of this linear map with respect to the spaces of these eigenvectors, was nice, meaning that it was just a diagonal matrix. And this we will do next time, and maybe also include some applications. See you then.